The following audio recording has been designed for learning purposes only. Do not share, distribute, or provide any type of copies, or this audio lesson will not be made available to you. Good luck with today's lesson.
So this means you have infinite solutions. And these are the only three possibilities that we can have. So again, we get one solution, no solution, or infinite solutions. And as you'll see in this class, we're only going to do 2 by 2, two unknowns with 2 equations. But when you go into higher dimensions as well, in your Math 1000 class, you'll do 3 by 3 systems. Same thing there. You get one, none, or infinite solutions. And it's going to be that way for any, whatever number of dimensions your linear system is, that's always going to be the case. So basically all the intuition we build up for just being able to solve these 2 by 2 cases, that intuition will basically carry on to, however many dimensions you might happen to be working in. So that's something that's nice about these linear systems is, these 3 possibilities here are all we can get. So it's the only thing we would have to worry about in that point. So graphically for us, this is basically it here. But as I said, graphing is not necessarily the best way to go about solving these. So now we want to talk about if we have a system of equations, say like this, we've just got our equations listed, how can we go about and solve it algebraically? Because, trying to solve it graphically would mean, you're either going to have some piece of technology or you want to have graphing paper and a ruler at the very least if you want to try to solve it that way. So in the next section, we're going to start looking at algebraic techniques for solving these systems of equations here. So this is section 5.2. So we want to be able to solve systems by substitution. So this is one of 2 algebraic techniques we're going to learn to solve these. So we're just starting here. So let's say, I'm just going to jump in with an example. Say I want to solve this. Okay. And again, especially now that we're going to be using algebraic techniques to solve these, I like to label the equations, in this case 1 or 2, A and B, whatever you feel like calling them, just so I can more easily refer to them. In the next section, when we look at a different technique, this will be more useful as well. Okay, so what am I going to do here to try and solve this? Well, in this section, we're going to talk about substitution. What we're going to do is I'm going to take one of the 2 equations, doesn't really matter which, and then I'm going to pick one of the variables. And again, it doesn't really matter which one. What you want to do is you want to kind of pick it so the algebra will be easy. So what we're going to do is pick an equation, pick a variable. We're going to solve for that chosen variable in terms of the other one. So we're just going to rearrange the equation to get one of the variables by itself. Okay. So that being the case, often what you'll want to do is you'll prefer this method if you can easily solve for one of the variables. Basically what that means in terms of the algebra here, you kind of want to only use this technique if the coefficients on one or more of the variables is positive or negative 1. Because then you won't have to divide through by anything and you won't be dealing with fractions. So again, it's just one of those situations where fractions are a little more cumbersome, so we would prefer not to work with that. So this technique is going to be preferred if you have coefficients on one or more of the variables that are just positive or negative 1. Because then you won't be dealing with fractions because you won't have to divide through by anything to get the variable by itself. So here we've got some choice. I could pick the first equation, and ideally I would want to solve for y if I use this equation. Or I could go with equation 2, and again, ideally, in this case, I would want to solve for x in terms of the other variables. And again, it doesn't matter which one you decide to go with. Let's just go with equation 1 and solve for y here. So that's what we're going to do first. So let's use equation 1 to solve for y in terms of x. So I've got equation 1. So I have negative 2x plus y is equal to negative 11. So I just want to get y by itself. So all I have to do is add 2x to both sides here. And we get y is equal to 2x minus 11. Okay, now what I'm going to do, I'm going to take this expression I have for y, and I'm going to substitute it into the other equation. So in this case, equation 2, I'm going to plug in this expression in terms of x into this equation. So replacing y by this expression here. And what's that going to do for us? Well, now what I've done is I've gotten rid of y in this equation. Everything is in terms of x now. So I've reduced it to one equation with one variable, and that's something we've seen before. We can solve that. It's just back with the chapter 2 stuff there. Okay. And then once we have x, well, once we have x, I can just go back and compute y directly. Okay. So that's the method here. We pick an equation, pick a variable, we solve for it. We then substitute that expression then into the other equation, the equation we did not use. And then we solve for, whatever variable we have in that equation, and then we can go back and get the other variable. So I'll write these steps down, but I'm going to work through this example first. So now we substitute this expression for y into equation 2. So it's got to be the other equation, the one you did not use in the first part. Okay, so y is equal to 2x minus 11. I'm going to plug that into, I have x plus 3y is equal to 9. So I would have x plus 3 times, now y is this, so that's 2x minus 11, and this is all equal to 9. So now I've got this new equation, and it just involves our variable x. So this is an equation that we can solve and get x now. So now solve for x. So here just need to distribute this 3, so we end up with x plus 3 times 2x, it gives me 6x minus 3 times the 11 is 33, is equal to 9. X and 6x gives you 7x, minus 33 is 9, we just add 33. So I end up with 7x is 42, and then just divide by 7, so we get x is equal to 6. Now we have x, so I can just plug that into this expression here for y, and then we compute y. Now plug in to get y. So y is equal to 2 times 6 minus 11. So 12 minus 11 is 1. So we get that y is equal to 1. So our solution then, x is 6, y is 1. So that would be the point 6, 1. Okay? So basically what we're saying then, if I plotted both these equations, I got the lines, we would see them intersect at the point 6, 1. And I'll do that on the computer here in just a second. So our solution is 6, 1. So let me pull it up just to verify that that's our solution here. Okay, so the equations were negative 2x plus y is negative 11, and x plus 3y is 9. And we can see they intersect. That point is 6, 1. So that would be our solution here, definitely. So that's the substitution method. So that's an algebraic method to go along with the graphing method that we had talked about before. So, so this would be something where if you didn't have technology or at least graphing paper, people could do that. So these algebraic techniques are going to be kind of the preferred method to use if we're doing it by hand. But the graph here is just a check. Okay. So this is our technique. So I'm going to write the steps down for this, but this is basically what we are doing here. So any questions on this? Okay. Well, let's write down what we're doing and then do some more examples. Okay, so what you do first is pick an equation and pick a variable and then solve the equation for that variable. So we solve one equation for either variable. Okay, so that was the first thing that we did. I picked the first equation and I solved for y in terms of x. Then we take this expression from step 1 and we substitute it into the other equation. Yeah. Is there a question?
No, it was blessed.
Oh, okay. 3. Okay, so now we solve this new equation. So solve the resulting equation. Then we substitute. So we'll get an actual number now. So we do that. So then we substitute the solution from step 3 into the expression from step 1 to find the other variable. Then you'll want to write the solution as an ordered pair. And it's always a good idea to check your solution as well. So I checked it graphically. We'll do an example where I'll check it algebraically. But I mean, to check that, all you do is you just check that the ordered pair satisfies both equations at the same time. So you just plug it in and check. But I'll do an example of that here in just a moment. Okay, so this is our substitution method. So are there any questions on basically the steps here? Does this seem all right?
Mm-hmm.
All right, let's do another example. Okay, so we have this system here. X plus 3y is equal to 10, and 4x plus y is equal to 18. So again, what we want to do is pick an equation and then solve that equation for one of the variables. It doesn't matter which. I'm just going to go with equation 1 and solve for x in this case, because again, what I want to do is I want to pick a variable somewhere in the system where the coefficient is just 1 or negative 1, because that's easier to solve for. So I'll just go with equation 1 and solve for x. So let's use equation 1 and solve for x. So I have x plus 3y is 10, so all I have to do is subtract 3y. And then we get x is negative 3y plus 10. Now I just take this expression for x and I'm going to plug it into equation 2. So now plug into equation 2 for x. So I would have 4 times x, x is this stuff here, negative 3y plus 10, and then plus y is equal to 18. Okay, so now we've got this new equation with just y, and we solve for y. So I have negative 12y plus 40 plus y is equal to 18. So negative 12y and positive y is negative 11y plus 40 is equal to 18. Subtract 40. So I get negative 11y that's going to be negative 22. Divide by negative 11. So we get y is 2. Now that I have y, I can go back and compute x, because we know x is just negative 3y plus 10. So now we use this to get x. X is negative 3y plus 10, so that is negative 3 times 2 plus 10. So it's negative 6 plus 10 is 4. So the solution, xy, is 4, 2. Okay. Any questions on that?
So if I'm understanding it correctly, you pick one variable
Mm-hmm.
and you solve for that one by like either subtracting or adding based on what you have to do to
Yeah, I mean, you're just solving for a variable.
yeah, and then you plug it into the other equation,
Mm-hmm.
then do your subtraction and division, and then
Well, you're just solving the equation, whatever steps you have to take.
yeah,
Because then you get the new equation with just one variable, so you solve it.
and then you plug in whatever numbers you come up with to
Yeah, so now then you solve for that variable. And then once you have this, whatever it is, what number you get, then you just plug it into the expression you had for the original variable that you solved for. And then you should have both numbers at that point. So yeah, so that's our solution. So let's actually check this one. Now that we have our solution here, so let's check. So the system was x plus 3y is 10, and 4x plus y is 18. This was 1 and 2, and the solution was 4, 2. So we're just going to check that this works. So for the first equation, I would have x plus 3y. So x is 4, so this would be 4 plus 3 times y is 2. And is this equal to 10? Yeah, it's 4 plus 6, which is 10. So it satisfies the first equation. And now we just want to check that it satisfies the second equation. So this would be 4 times x, which is 4, so 4 times 4, plus y, which is 2. Is that equal to 18? Yeah, because we get 4 times 4 is 16, and then plus 2 is 18. So that also checks out. So 4, 2 satisfies both equations at the same time, therefore it's the solution. And again, if you want a visual check, we can do that as well, real quick. So it's x plus 3y is 10. 4x plus y is 18, and 4, 2. We can see that graphically we get the same confirmation there. So this 4, 2 is the solution there. Okay, so any questions on that? Okay. Let me give you all one to try then. So go ahead and solve. Okay, go ahead and solve that one and see what you get here. Okay, how many people have a solution? Okay, what do we get?
One negative.
It's
1, negative 2? How many people got 1, negative 2? Okay, good. So let's go ahead and run through it. So I think the equation we want to solve for to start out with is probably, which one did you go with here? First equation, and solving for what? Y, yeah. So that's the only variable that has a coefficient of 1 or negative 1 in this case. So that's kind of the obvious choice that we want to make here. So we're going to use equation 1 and solve for y. So I have 4x plus y is 2. So just subtract 4x. Whoops. So we get y is negative 4x plus 2. Then we take this expression for y and then plug it into equation 2. So taking this and plugging it in here. So from equation 2, I have 3x plus 2 times all this stuff, negative 4x plus 2 is negative 1. Then we just solve this for x. So it's 3x minus 8x plus 4 is negative 1. So the 3x minus 8x gives us minus 5x plus 4 is negative 1. Subtract 4. Negative 5x is equal to negative 5. So divide out the negative 5 and we get x is equal to 1. Now that I have x, just plug it in here for y. So y is negative 4 times 1 plus 2. So that gives us negative 4 plus 2 is negative 2. So we get y is negative 2, and then the solution is 1, negative 2. And quick visual check. Again, if you graph those, we can see they intersect at 1, negative 2 here. So that's just a visual check for this one. Okay, questions here? Okay. So again, this is substitution, and I would say only use this one when it's where you can easily solve for one of the variables. So again, when one of the coefficients on at least one variable is plus or minus 1, because then it's just easy to solve for that variable. Okay. Now there are some cases where if you're given a system where one of the variables is already solved for, I mean, just make use of it. So an example like that is, say, something like this. So suppose I have x plus y is equal to 6, and y is equal to 3x minus 2. Okay. So sometimes you might see something like this. Well, in this case, one of the variables is already solved for. Like one of the equations you're given is basically setting you up to just go ahead and solve this by substitution. So obviously when that happens, just take advantage of it. So we've already got our substitution that we want to make. We have y equals 3x minus 2 that was given to us. So just use it. So just immediately plug in this expression for y, plug it back into equation 1 in this example here. So we just use equation 2 to plug in to equation 1. So we have y equals 3x minus 2. just go ahead and plug that into equation 1, which is x plus y equals 6. So we would have x plus y, and y is this stuff, 3x minus 2, and this is all equal to 6. So we've got this, so it's x plus 3x minus 2 is 6. So we get 4x minus 2 is 6. Add 2. So 4x is equal to 8. Divide by 4, and we get x is equal to 2. So we have x, and now we just have y is 3 times 2 minus 2. So 6 minus 2 is 4. So we get 2, 4 for this solution here. Okay. So again, if you're kind of given if you're given an assist here, just take advantage of it. So like this. Now some examples, I mean, again, in this case there's still no fractions here. But even in the case where, say, y is equal to a half x, so let's look at an example like that, it's still going to be pretty useful to take advantage of. So in that case, you would still probably want to use this. So if I want to solve this one, suppose I have, that's fine, y equals negative x plus 10, and y equals 1/4 x. I mean, you could go either way here with how you want to do it. Now this has a fraction, but again, when it's kind of set up for you like this, just go with it. There's no reason not to. So y is 1/4 x, so I'm just going to plug this in to my first equation here. And then we can solve for x. So this is 1, 2. So I'm just going to sub y equals 1/4 x into equation 1. So I would have 1/4 x is equal to negative x plus 10. Okay. Now this equation has fractions, and I prefer not to deal with that. Well, this just has a denominator of 4, and there's no other fractions in this equation. So I'm just going to multiply both sides by 4 to get rid of the fraction here. So I'm going to do 4 times 1/4 x is equal to 4 times the quantity, negative x plus 10. So here, the 4's drop out, so it's just x is equal to this over here. I'm going to distribute, so it'll be minus 4x plus 40. Now I just want all my x's on one side, my constant on the other. I'm going to add 4x here. So I get 5x is equal to 40. Divide by 5, and we get x is equal to 8. Now that we have x, we can just go ahead and sub back here. So y is 1/4 times 8. So 4 simplifies, and that's 2. So we get y is equal to 2. So the solution is 8, 2. Oops. Bless you. Okay, any questions there? Okay, so all of these examples, these were all examples where we had one solution. Okay. So next, what we want to talk about is, well, what does it look like if we're grinding through one of these algebraic ways of solving it? What would it look like in the case where we would have no solution or infinite solutions? Okay. So I just want to show you a couple examples of that. But first, let's go ahead. Let's take a short break. We'll come back, and then we'll look at those cases just to see what they look like algebraically when you're solving these. Let's take a few minutes break right now. Okay. Okay, so we've got this example here. So in this case, none of the variables have a coefficient of plus or minus 1, so we're just going to have to deal with it in this case. I'm going to go ahead and solve. I'm going to just use equation 1. I'm going to solve for x. Okay, doesn't really matter what I decide to go with here. That's just what I'm going to do. So in equation 1, we have 2x minus 3y is 12. I'm going to solve for x, so I'm going to add 3y to both sides. So then I would have 2x is equal to 3y plus 12, and then we need to divide both sides by 2. So we get x is, it's going to be 3 halves y plus, and then 12 divided by 2 is 6. So we get this. X is equal to 3 halves y plus 6. Now I'm just going to take this expression for x and plug it into equation 2 here. Okay, so plug this into equation 2. So I would have negative 12y plus 8 times the quantity, 3 halves y plus 6 is equal to 48. So I have negative 12y plus, then I would have 8 times 3 halves y plus 48 is equal to 48. Okay, here. Now I just want to simplify this. 2 drops out there. 8 simplifies to 4. So what I have is negative 12y. And then this is positive 12y, so plus 12y plus 48 is equal to 48. And what we see here now is the variables drop out completely because the negative and positive 12y cancel out, and then I'm just left with this. 48 is equal to 48. And this is just a true statement. No matter what, this is always true. So we've seen this before. Remember when we had one variable in one equation, when we ended up with a statement that was just always true, that implied we had infinite solutions, right? So I can pick any, because y dropped out here, so it didn't matter what y was. We just ended up with this statement, and that's always true. So this implies that we have a system of equations with infinite solutions in this case. So geometrically what that would mean is, if I graphed both these lines, they're actually the same line. They're just lying on top of each other. So any point on the line is a solution. So again, this is what we call an identity. So this implies that we have infinite solutions. Okay. So just like in the single variable case, if you remember for those no solution or infinite solution scenarios, that was when the variable dropped out, and then you were just left with either a true or a false statement, right? It would be, well, something true like this, or something false, like 0 equals 1, or whatever. Okay? So in the case where it's a true statement, that implies infinite solutions. The other case, when there's no solution, you get something like 5 equals negative 10, maybe something like that. And that's obviously always false.
What if you solve it without dividing by 2?
Sorry?
What if you solve it without dividing by 2?
Oh, so... I mean, if I left this as 2x equals... So 2x is equal to 3y plus 12. Like this. Well, then if I wanted to... Because then I wouldn't be substituting for x, I would have to substitute for 2x, right? So this 8x term here, what I could do is I could rewrite it as 4 times the quantity 2x. And then I could sub in, for 2x I could substitute this in. But you're going to end up with the same thing. All the arithmetic and everything is going to work out the same. It's still going to be infinite solutions here. Okay. So, I mean, you could do that if you want to. Maybe you're making it more complicated than it needs to be, though. Because then whatever number is out front of the x here, you have to make sure you can rewrite this quantity so you can substitute for what you actually have here. Okay. You have to match this up. I mean, because this isn't x, it's actually 2x. So it means you have to substitute for the expression 2x in this case. Which you can do, but you might be making it a little bit harder on yourself than you would need to. So we get this. And real quick, let's just graph it to see that these are what I said they were. So we had 2x minus 3y is equal to 12, and negative 12y plus 8x is equal to 48. And we can see they're just the same line. So any point on that line is a solution. Lines have an infinite number of points on them, so infinite solutions in this case. So that's what we see here. Okay. Well, then what is an example going to look like when there's no solution? Well, again, similar to this, we'll see the variables drop out, but we'll be left with a false statement at the end. So in this case, we got 48 is equal to 48, which is obviously true. In another case, when there's no solution, again, it'll be something like 5 equals 10, or, just something that's always false. But let's see an example of that real quick. So let's say we want to solve this. So say I have 3x plus 2y is 9, and y equals negative 3/2 x plus 1. So again, this is kind of a obvious choice. One of the equations is just given to us ready to make a substitution, so we're just going to use that. So I'm going to plug equation 2, where y is equal to minus 3/2 x plus 1. I'm just going to plug that directly into equation 1 here for y, and then we'll see what happens. So I'm just going to plug this in here. So I would have from equation 1, 3x plus 2 times the quantity minus 3/2 x plus 1 is equal to 9. Okay, so then I would have 3x plus, it'll be 2 times minus 3/2 x plus 2 is equal to 9. The 2's drop out, and then this will be 3x. This is a minus 3x now, so minus 3x plus 2 is equal to 9. And we see now the x's drop out, and we just are left with the statement 2 equals 9. So that's obviously always false, and it doesn't matter what value of y or x we pick, that's always a false statement. So this is false. Or we've seen this term before. This is what we call a contradiction. And this means that we have no solutions, or no solution. So geometrically, what does that mean? If I were to plot these lines, what would that look like? Yep, these are parallel lines. So let's just verify that real quick. Yeah, so again, in terms of, lines in the plane, when there's no solution, that means the lines don't intersect, so that means they are parallel. So we can check that real quick. So we had 3x plus 2y is equal to 9. And we had y equals minus 3/2 x plus 1. And we can see these lines are parallel, so they never intersect anywhere. There's no solution. Okay. But algebraically, that's what we see. Again, we see these concepts of identities and contradictions coming up, and that tells us whether we have no solution or infinite solutions in that case. And it'll be the same thing in the next section when we talk about using a different algebraic method for solving these. Okay, so this will come up again. But let's actually go ahead and talk about that now. So are there any questions here on substitution method for solving equations here? Seem all right? Okay. Let's talk about our other algebraic technique then. So this is what is called the elimination method. So this is section 3. So we want to solve systems by what's called elimination. Okay, so this method will probably be preferred when None of the coefficients of the variables are positive or negative 1. Okay. So substitution method was nice when we could easily solve for one of the variables in terms of the other. If that's not the case, you might prefer using the elimination method. Now again, it's just a preference. It just depends on which method do you think will solve it the easiest for you. I mean, these are equivalent. I mean, if I use the elimination or the substitution method for a system of equations, as long as I do everything correctly, you're going to get the same answer either way, right? I mean, because if two lines intersect at a point, it's always the same point. It doesn't matter what method you use to figure out what that point is, okay? So again, as long as you're doing everything correctly, all these methods for solving these are equivalent to each other because it's all going to lead to the same answer in the end. So first, for expressions, let's say A, B, C, and D, we have if A is equal to B, and again, these could be more complicated expressions. I'm just using A, B, C, and D as placeholders here. We'll see some examples why in a minute. So if A is equal to B and C is equal to D, then the following is true. I can add A and C together, and that's equal to B plus D. So if A is equal to B and C is equal to D, I can add A and C together, and that's equal to B plus D in this case. This is just saying we can add expressions together, and we still maintain equality here. So, again, first I'm going to do an example, and then I'll write the steps down here. Okay. So this is called the elimination method because our goal is, what we want to do is I'm going to basically add these equations together in such a way that one of the variables will drop out or be eliminated. And then I'll get a new equation with just one variable that I then solve, and then I can go back and figure out what the other variable needs to be. So for this method, we want both of our equations written in standard form. So like this, in this case. We'll see some examples where we might have to change it around a little bit. But we need both equations in standard form. And then we also need to line up the x's and the y's here. Okay. Now again, I said our goal is, I want to add these equations together so one of the variables drops out. Well, to do that, what I'm going to need is I will need the coefficients on either the x's or the y's to be negatives of each other. You know, one would be like, say, +5, the other coefficient would be -5, so that when I add the equations together, that particular variable will drop out. Now that's not the case here, but again, remember, for these linear equations here, if I multiply both sides of the equation by just a number, it's still the same equation, right? We know that equations that are just multiples of each other are still the same equation, right? We know that when we go graph it, that's the infinite case solution, right? So that means I could take either or both of these equations, multiply each one by a non-zero number, and they still represent the same line or equation for the what we're trying to solve here. So that means I can multiply one or both equations by a non-zero number to try and get the coefficients on one of the variables to be negatives of each other. And then when I add those results together, I get one of the variables to drop out. Okay? So in this case, I have a positive 3x and a positive 2x here. Now normally what you're going to do is use the least common multiple for whatever numbers you see here. Okay. But in this case, what I'm going to do is, I'm not going to bother to try and get the x's to drop out. I'm going to look at the y's here, because I have here, they're already opposite sign. This is a negative coefficient here. This is a positive one here. Now this is a negative 3y, so that means I want the coefficient on this y to be positive 3. So what I'm going to do is I'm just going to multiply the whole equation through by positive 3. Okay? Now I can't just multiply one part of the equation by that number. It has to be the whole equation. So what I'm going to do is take equation 1, multiply through by positive 3, and then I'll get my result, but I know the coefficient on my y will be positive 3 here. So then I'll take my new equation, and I'm going to add it to equation 2 to get my y's to drop out here. So let me write that down. So we want the coefficients on one of the variables to be negatives of each other. So what I'm going to do is I'm going to take equation 1 and multiply it by 3. So this is my notation I like to use. I have equation 1, I'm multiplying it by 3, and then I'm just going to add that directly to equation 2. Okay. So just like we've seen before, I'm just using the 1 and the 2 here to refer to equations 1 and 2. So multiply equation 1 by 3, take that result, add it to equation 2. So I have 3 times equation 1, so that's 3x plus y is equal to 3 times 5. So I get 9x plus 3y is equal to 15. And then I'm just going to add equation 2 as it is. And again, I need these in standard form, and I have to line up the variables and the equal sign and the constants like this. Okay. Now I just add these vertically. So 9x and 2x gives me 7x. And the positive 3y and negative 3y, well, that drops out. That gives me 0. Which that was our goal here. I wanted to get one of the variables to drop out, and I did. The y's are gone now, and I'm just going to have something where 7x is equal to, it's going to be what, 22?
Is it 9 plus 2, 11x, right?
11x?
Yeah. I don't know why I subtracted those. That's better. Sorry, yeah, 9 and 2 makes 11. I don't know why I subtracted those. Okay, so we have 11x is equal to 22. So x is equal to 2. Okay, now what I'm going to do is, now that I've got one of the variables I can just go back to my original equations, plug in that value for x in this case, and then I can solve for y. Now when you go back to take this value and plug it into one of the original equations, it doesn't matter which equation you use. You can use either one. So whichever one where you think the arithmetic might be easier to solve for the last variable, you can just go ahead and pick that one. If it doesn't look like one is necessarily easier than the other, just flip a coin. It doesn't matter. But we have this. So x is equal to 2. Now in this case, I'm going to pick equation 1 because y will be easier to solve for in this case. Okay, so again, if one makes it easier to do the calculation, just go ahead and pick that one. If it doesn't matter, it doesn't matter. But in this case, it'll be a little bit easier to go with equation 1 here. So now plug into one of the original equations. So I'm going to use equation 1. So equation 1 was 3x plus y equals 5. And from before we had that x is equal to 2. So we have 3 times 2 plus y is equal to 5. So 6 plus y is 5. Subtract 6, and we get y is equal to -1. And now we're done. So we have x and y. So the solution is 2, -1. Okay, so that's an example of the elimination method here. The goal is to take either or both equations, if necessary, multiply each equation by a non-zero number so that the coefficients on one of the variables will be negatives to each other. Now often this is going to be the least common multiple. Okay? So in this example, we could have also, if I wanted to eliminate x, well those coefficients there are 3 and 2. So what's the least common multiple for 3 and 2? 6. Yeah. So what I would want to do is I would want to pick numbers so that when I multiply this equation through by a number, it's either going to be 6 or -6. And then same idea here. Okay, so say for example, if I multiplied equation 1 by +2, let's say, then the coefficient on this x would have been +6, after multiplying it out, right? And then I would have wanted to multiply this equation by what? -3, so that the coefficient on my x here, again, after I multiply through, would be -6. Then I would take those results, when I add them together, well, this would have been +6, this would have been -6, so my x's would have dropped out, and then I could solve for y. Okay? So again, it doesn't matter which variable you decide to get rid of, but, pick the one that'll be easiest. In this case, the coefficient on this y was -3. This was +1, so the only thing I had to do was just multiply the first equation by 3. And then I could just add directly. So just take the path of least resistance in that case. Now again, this system of equations here would have also been a good candidate for just using the substitution method, because we could have also just solved equation 1 for y here. Okay? But again, these methods are equivalent as long as you're doing everything correctly. It's the same either way. But we'll see examples where coefficients aren't always going to be positive or -1 here. When that's the case, you're probably going to want to go with the elimination method for trying to solve these, because it avoids having to deal with fractions a lot of the times. So, as we saw with the substitution method, if we don't have at least one coefficient on one of our variables, positive or negative 1, we may have to deal with fractions. And, you know, we prefer not to do that if we don't have to. But well, first let me write the steps out now, and then we'll do some more examples. So, how to solve by elimination. Depending on your book, this may also sometimes be referred to as the addition method, because you're adding the equations together. So these terms are equivalent. Some books call it the addition method, some call it elimination. Your book calls it elimination, but you know, if you're out reading stuff and they say addition method, it means the same thing there. So it's another common term for this method here. Your book uses elimination, and I think that elimination seems to be more popular now, but this one still comes up. Okay, so first, as I said, to use this method, both equations need to be in standard form. So that means your x's and y's on one side of the equation, your constant on the other. And also, if there are fractions, clear those fractions out. Okay, so you want to get it in standard form with the fractions there. So write both equations in standard form. If necessary. And also, if there are fractions, go ahead and clear those out. You know, multiply both sides by the lowest common denominator of those fractions. Again, if necessary. So if there are fractions, clear them. So just make sure everything's in the proper format first. Two, now what we want to do is make the coefficients of one variable opposites. So decide which variable you want to eliminate. And then you may need to multiply one or both equations by a non-zero number to make coefficients into opposites. Now add the equations from step 2 If you did step 2 right, that will get rid of one of your variables there. So remember, at this point, if you add them together and one of the variable you were trying to get rid of, if that doesn't drop out, then you made a mistake somewhere. Then, well, you should have a new equation with just one variable, so then you just solve for the remaining variable. Then after you get one variable, then what you do is take the value you got, go back to one of the original equations. I mean, it doesn't really matter which one. If you think one would be easier to use than the other, take that. And then figure out what the remaining variable is. Okay, so substitute the solution from step 4 into one of the original equations. And then solve for the remaining variable. And then write the solution as an ordered pair. And again, always a good idea to check. Okay. So any questions here on the steps or anything? Yeah.
What was the reference
That? Is that what you needed? Okay.
I think y'all written down.
Say what?
I think y'all written down as well.
Okay, yeah, sorry. Okay. So let's do some examples. Okay, so I have this system of equations here. 4x minus 3y is equal to 1, and 5x minus 9y is equal to negative 4. So in this case, we would probably not want to use substitution, so this would be a good reason to use the elimination method here. So which variable should we try to eliminate?
Y.
Y. Yeah.
Because you would multiply the top one by -3 to make that a +9, and then they cancel out.
Yep, exactly, yeah. So if I choose to eliminate y, I only have to multiply the first equation by, in this case, I would use -3. If I wanted to eliminate x, well, between 4 and 5, least common multiple is 20. So I would have to multiply both equations by something. You know, like the first equation, I would multiply by, say, -5, and then the second equation, I would multiply by a +4. So it's less work to eliminate y in this case. So again, pick things to be as simple as possible. You know, try to make it easy on yourself where you can. So if we just choose to eliminate y, I only have to multiply the first equation by something. The second equation I can leave alone. So that's what we're going to do. So I'm going to take equation 1, and I'm multiplying by -3. Why -3? Why not +3?
Because the two negatives will cancel out and you get a positive.
Right, because in the second equation, the coefficient is already negative. So that means for the first equation, we would want the coefficient to be positive. So in this case, that means we multiply through by -3. So what I'm doing, again, this is my notation, it's basically just stating what we're going to do. I'm taking equation 1, multiplying by -3, and then whatever this result is, I'm just going to add equation 2 directly. I'm not multiplying it by anything. So let's do -3 times all this. 4x minus 3y is equal to -3 times 1. So just multiply both sides of that equation by -3, and then I get -12x plus 9y is equal to -3. And then I'm just adding equation 2 as it is, so that's 5x minus 9y is equal to -4. Let's see if I added up the x's right this time. -12x and +5x would be -7x. Yes, -7x. And then the y's drop out. So -7x plus 0, and -3 and -4 makes -7. So we have -7x is equal to -7, and then when we divide that out, we get x is 1. And now we're going to take this value for x, pick an equation, doesn't really matter which one, plug in that value for x so we can get y. I'm going to use equation 1 because it doesn't really matter that much. So now we're going to plug x equals 1 into equation 1 and, whoops, solve for y. So equation 1 is 4x minus 3y equals 1. And we're going to plug in x equals 1. So I would have 4 times 1 minus 3y is equal to 1. So 4 minus 3y is 1. Subtract 4. So I get -3y is equal to -3. And divide that out. So we get that y is also equal to 1. So the solution is 1, 1. Okay, any questions there? And let's just check this one real quick. So what was it? Okay, so a quick check here. Our two equations intersect at 1, 1. So that's the solution for these. Okay, so questions? All right. Here's one for you to try. So let's see what you come up with. So they're both already in standard form and there's no fractions. So just go ahead and solve that, see what you get. Okay, how many people got a solution? Okay, what'd you get?
1 and 3.
1, 3?
1 and 3.
1, 3? Okay. All right. So, let's see. So what do we want to do here? So it's already in standard form. There's no fractions. Which variable should we eliminate? Hmm?
Why?
Y. I mean, yeah,
I've eliminated X.
you can do that too. I would go with Y only because they're already opposite signs. The X's both have positive coefficients. I mean, it's not wrong. It's just that the Y's, one coefficient is -4, the other one is +3. They're already opposite signs. That's the only reason I would choose those.
Okay.
But it's really not that different. You could go with X, and it's not going to change anything.
So would you have multiplied them by like 12 as an easy
Well,
way?
12 is the least common multiple between 4 and 3. So that means I want one to be -12, one to be +12. So for this equation, I'm going to multiply by what? I'm going to multiply by +3, because then the coefficient of my y will be -12. And then this equation I'll multiply by +4, because then the coefficient of my y would be +12. So then when I add them up, my y's will drop out. So in this case, we have to multiply both equations by something. The previous examples, we only needed to do that with one equation. But here, no matter which variable we pick, we're going to have to multiply both equations by something. So what we're doing is I'm taking equation 1 and I'm multiplying by +3. So I would do 3 times equation 1. And then I'm taking equation 2, I'm multiplying by 4. So it would be 4 times equation 2. So what I'm doing is taking equation 1 and multiplying by 3, taking equation 2 and multiplying by 4, and I'm adding those results together. Okay, so this is basically our little plan for what we're going to do with these equations. So first, let's take equation 1 and multiply by 3. So I have 3 times 3x minus 4y is equal to 3 times -9. So we would get 9x minus 12y is -27. And then we're going to take the second equation and multiply by 4. So I would do 4 times 5x plus 3y is equal to 4 times 14. So we would get 20x plus 12y is, what is that? 56, thank you. Okay, now I just want to add these two results together. So adding 9x minus 12y is -27. $20x and 9x gives you 29x. Y's drop out. And 56 and -27, is that 29?
Yes.
Thank you. So we get 29x is equal to 29. Divide by 29 so that we get x equals 1. Now that I have x, I'm just going to go back to one of the original equations. Doesn't matter which one. Plug in that value for x to get y. I'm going to use equation 2 just because in the previous two examples I used equation 1. So we have 5 times x, which is 1, plus 3y is equal to 14. So 5 plus 3y is 14. Subtract 5, so we get 3y is 9. Divide by 3, so we get that y is 3. So then our solution is 1, 3. And just a quick visual check. So we've got our two equations, and they intersect at 1, 3 there. So that's the solution. Okay, questions on that?
I have a question.
Yeah.
I canceled out like the x's.
Uh-huh.
I did -5 and then I did like 3 to cancel them out. I got the same answer. Like that's
Yeah.
fine to do that, right?
Of course, yeah.
I did the same thing, so
Yeah.
I ended up doing what you did and got the same thing.
Yeah, like you can choose, it doesn't matter which variable you decide to try to get rid of.
Yeah.
Again, as long as you do everything correctly, all the steps,
Yeah.
it's going to come out the same.
Okay.
Okay. And again, the only reason I would have gone with y in this situation is because they're already opposite signs.
okay.
That's the only reason. And I mean, that's really not that big a deal. You can just get rid of the x's. It just means you got to multiply one of the equations by a negative number instead of a positive.
Okay.
But I mean, it's not that big a deal. That's the only reason I did it, and it's just preference. Okay, any other questions here? Okay, let's take a quick break and see what we get here. Yeah. Okay. So again, just pick a variable to get rid of. Doesn't really matter. Let's go ahead and eliminate x. So for each equation, one has a negative 3x. The second one has positive 9x. So what I can do is I'm just going to take the first equation and multiply by 3. Because then the coefficient on the x there will be negative 9. Coefficient on x in the second equation is positive 9. So then when I add those together, the x's will drop out. So I'm doing 3 times equation 1, and I'm just adding that directly to equation 2. So 3 times negative 3x plus 2y is equal to 3 times 8. So I get negative 9x plus 6y is equal to 24. And I'm just adding equation 2 directly. So that's positive 9x minus 6y is equal to 13. And you might have noticed what's going to happen here.
Both cancel out.
Both variables drop out in this case. So same thing would have happened. If I would have chosen to eliminate y, x would have also dropped out, because what would have happened? I would have multiplied first equation by 3. Same thing. So over here we're going to get 0. Over here we're going to get what? 37?
37.
So we get 0 equals 37. So obviously this is a contradiction. So that means we have what? How many solutions?
No.
No solutions, right? In other words, these lines are parallel if we were to plot these. Similarly, if there had been infinite solutions, I also would have gotten 0 over here. So these things would cancel out exactly too, along with all of the variables. So in the case of infinite solutions, you'll just get the variables will drop out and the constant terms drop out. And you just end up with 0 equals 0, which is, that's always true. So in that case, the equations are just multiples of each other. So when you try to eliminate one of the variables, you basically just cancel everything out because they're the same equation, really. So that's what you would expect to see in this case. So that's the elimination method. So are there any questions on that in general? Okay. So let's go ahead and jump to the next section. So we'll probably only have time for a couple examples here. But we'll see what we can do. Okay, so again, with all of our story problems, problem solving, we're going to take all those ideas and we need to come up with, in this case, we're going to define two unknown quantities, usually our x and our y, and we will need to come up with two equations so that we can solve those. So we need to be able to write equations down, if we're told certain information and all that stuff. So let's just jump in with some examples here. So let's say a senior employee makes $5 less than twice what a new employee makes per hour. Now together, they make $43 per hour. How much does each employee make? Okay, so again, there are two unknown quantities we want to find. We want to know what the senior employee makes per hour, and we want to know what the new employee makes per hour. Those are our unknowns. It doesn't really matter what you call them. Let's just call them X and Y. So let's say that X is the senior employee rate, pay, wage, whatever, employee wage, and Y can be the new employee wage. Okay, So let's actually write down, let's go to the second part here. Together they make $43 per hour. So that statement tells us what? That gives us an equation. What would I write down?
2x minus 5.
No, just this statement
just-
here.
oh.
Together they make $43 per hour.
So it would
X
be
plus
plus
Y.
X plus Y equals, yeah. So the hourly wage for the senior employee plus the hourly wage for the new employee has to come out to be $43 per hour.
Okay.
So that just means X plus Y is 43. So that's one equation. So X plus Y is 43. Together they make $43 per hour. Okay, and now we want to go back and look at, okay, the first sentence there. A senior employee makes $5 less than twice what a new employee makes per hour. Okay, so that tells us the senior employee, so that's X. X is equal to, well, it's in terms of the new employee.
So 2y minus 5.
Yep, so $5 less than twice what the new employee makes. Well, twice what the new employee makes is going to be 2y. And we want $5 less than that, so we subtract 5. So we're going to have that X is equal to 2y minus 5. Okay, so the senior makes $5 less than twice the new. Okay, well, these are the equations. We have X plus Y is 43, and X is equal to 2Y minus 5. You can use whatever method you want when you're solving these. This one, we already have an obvious substitution that we can make, so let's just go ahead and do that. Okay, so let's just, I can call this 1, and this can be 2. Let's just substitute 2 for X in equation 1. So for equation 1, I have X plus Y is equal to 43. So we want to sub X equals 2Y minus 5. So I would have 2Y minus 5 plus Y is equal to 43. Now I just need to solve that equation. So I would have what? 2y and y is 3y minus 5 is 43. Add 5. So you get 3y is what? 48? Then divide by 3. Yep. So we get y is 16. And now that I have y, I can get x. So x is 2 times 16 minus 5. So 32 minus 5 is 27. Okay. So the senior employee is making $27 per hour, and the new employee is making $16 per hour. So 27 and 16, does that add up to 43? Yep. Okay. So that's good. So the senior makes $27 per hour, And the new employee makes $16 per hour. Okay, any questions there? Is all right? Okay. Okay, see if we can get a couple more in. Okay, a couple things here. So some terms just to help us with some of these here. So we say that two angles are complementary if their angle sum is 90 degrees, and we say that two angles are supplementary if their angle measure is 180 degrees. So, well, that means in these problems, suppose I have two unknown angles, but we're told up front that they're, say, complementary or something. Well, if I have two unknown angles, call one x and one y, as soon as they tell me one of these statements, if they tell me that angles are complementary, then I would have to know x plus y is 90. I mean, that's one equation you're given, essentially. If I told they're supplementary, then I would say x plus y is 180 in that case. So for these problems, often it'll say the difference of two complementary angles is, say, 20. Okay. Well, they told you they were complementary, so that's one piece of information I already gave you. And then they told you that the difference between the angles is, this other number. So for these types of problems, just using the word complementary or supplementary is basically already giving you one of the equations that you need. And then you just say, okay, well, then they told me the difference is this. Well, difference means x minus y, and then you set it to whatever number they told you. So again, as long as you understand what these terms mean, these particular problems should be pretty straightforward. Okay. So let's just try an example here. Let's say the difference between two complementary angles is 20 degrees. Find the angles. Okay, so notice here it's assuming you know what complementary means, because that just tells you, that gives you enough information to write down one equation. So again, let's just define our variables. Let's say that x is one angle and y is the other angle. Now, from them being complementary, bless you, just being told they're complementary, that tells us that x plus y is 90. So that's one equation. So x plus y is 90. That just comes from the fact that we're told they're complementary. Okay, and then we're told, well, their difference is 20. So for that, I would write what down?
X minus y equals 1.
X minus y is 20. Okay. And the way it's worded here, I could write y minus x is 20 as well. It wouldn't matter, okay? Because we're not, I mean, the angles aren't named, we're just told we have two angles, we want to figure out what they are, okay? So if you had written y minus x equals 20 instead, you're still going to come up with the same answers. I mean, your x and y's will be swapped, you'll get different, they'll be exactly different compared to the way we solve it here, but it doesn't matter. I mean, we're just told we have two angles. It doesn't matter if we say x is one or x is the other. All we care about is finding them. Okay, well, we can solve this, and we can do it very easily. If I just add these together directly, the y's will drop out. So I'm going to use elimination here. So add those together, y drops out, and then we can get x. So this is their difference. That's where this equation comes from. And I'm just going to add these, so I get 2x plus 0 that's going to be what, 110? So 2x is 110. Divide by 2. So x is 55. Okay, so one of the angles is 55 degrees. Now we want the other one. So can just use this equation here. I know that x plus y is 90, so that means 55 plus y is 90. Subtract 55. So we get y is, that's going to be what, 35? Okay, so that means one angle is 55 degrees. The other is 35. Okay, any questions there? Okay. So the other ones are going to be harder. Okay, so we're actually going to stop here for today. Okay, so this could be what you can expect to see on the exam. So remember, we do not meet next week, right? We have our spring break, winter break, whatever you want to call it. So see you in 2 weeks. So the exam will be everything we covered in Chapter 4, which I think we did everything in Chapter 4. And then in Chapter 5, it'll be the first 3 sections. And then for this section on applications, you can expect to see examples similar to what just these examples that we did in class today. We'll do more examples next time, but expect to see something involving angles or something similar to the first example there as far as applications go. All right? So that's what will be on the exam, and it'll be just like last time, a lecture for like the first half of class, and then we'll do the exam at the end.
20 questions as well, or is it more?
Yeah, it'll be 20 questions. So yeah, 20 multiple choice questions. Make sure you have a red Scantron number 2 pencil. Okay, I'll see you all. Enjoy your break. I'll see you in 2 weeks.
Good luck with today's lesson.